Hello, my name is Jason Gregerson, and this video is going to discuss modeling the position of a mass attached to a spring over time, and we're going to model this with differential equations. So to start off with, we need a spring. First picture here, I have a spring. I'm going to take that spring and attach a weight to it. That weight is going to pull it down some distance, which I'm going to call S. Eventually, it'll come to rest there at equilibrium. Now from there we want to talk about the position of this mass if, say, we pull it and let it go, and the position at any given time. So we'll look at that position from its equilibrium position. We'll say that distance is going to be some value x. Now because we're going to talk about its position, we want to kind of throw a coordinate system onto this. So the one that we're going to choose to work with, so we're going to say that, draw a little line through our equilibrium position and say that's our 0. And anything below that equilibrium position is positive, and above is negative. So basically down is the positive direction, and up is the negative direction. So once we've established that condition, that convention I should say, we can go ahead and further model this. So where we're going to start from is a classic equation. Force is equal to mass times acceleration, which we can rewrite the right hand side to say that's mass times second derivative of position with respect to time. Since the mass is going to be fixed, remember that mass is attached to the spring, and we're trying to find out what the position is, what we really need to determine is what are the forces involved. Now what we're going to look at first is a very simplistic case. We're going to assume that there are no forces from the medium around. For instance, there's no wind resistance, and those outside forces are taking effect. So the only forces that we're going to look at in this case are the downward force by gravity and the force provided by the spring to fight against gravity. So we have gravity. So we're going to look at our equilibrium position. We're going to say that at that position we have a force downward and a force upward. We know those forces are equal because the spring is sitting in equilibrium. So the downward force is mass times gravity, and the other force is going to be the spring force. Hooke's law tells us this is proportional to the distance the spring is stretched. So that means it's equal to some constant times the distance the spring is stretched. In this case, we call that S. So this is our first relationship we're going to look at. I'm just going to rewrite that as mg minus ks is equal to 0. So that's our first little relationship. That's for equilibrium. Now if we look at where that mass is in motion, we're looking at position versus time. We're going to say that at some time here we have the mass times gravity, that force going downward, and the force upward is going to be that constant k times the total stretch of the spring. In this case, we're going to have that initial distance s plus whatever the position is at any given time, because k becomes a quantity s plus x. So that's at any given position, so those are the forces that are involved. So in other words, we have the force is mass times gravity, that's our downward force, and the upward force, we have a negative sign here, is that k times s plus x. Okay, so now we distribute, and that gives us mg minus ks minus kx is equal to mass times the second derivative of position with respect to time. And here we can identify, right there are those terms, mg minus ks, is what we already established, this was just 0. So what we're left with is mass times the second derivative of position with respect to time is equal to a negative k, spring constant k, times the position. So I'm going to rewrite that one more time and say this is just, I'm going to add that kx to the other side and then divide by m. So that's the equation I'm left with. And I like that because what I'm looking at now is just a second order linear differential equation, because I know that k is a constant and m is a constant. I have constant coefficients, and I know how to solve these. And so that's basically what I'm going to do. But instead of solving it generally, I'm going to look at some specific numbers, see if we can work through a problem, and then discuss the solution. So what we're going to do is look at this case.